Okay, today we are going to start a new topic, and that topic is Fourier transform. Fourier transforms. Fourier transforms. This theory of Fourier transform has wide applications in physics. It can be used to analyze a signal which we receive and then find out the frequencies which are present in the signal, that is the components which are present in the signals, and what is the amplitude of each frequency that is present in the signal. That can also be analyzed using this method. Then this method can also be used to solve differential equations. Okay, so first let us understand what Fourier transforms are. So if I have a function f of t, suppose I have a function f of t, small f of t, then the Fourier transform of this function, the Fourier transform of this function is given by 1 by root 2 pi integral f of t e to the power minus I omega t dt. And this we shall represent by capital F omega. So this is the Fourier transform of the function f of t. Okay, that is fine. So this is the Fourier transform of the function f of t. Now let us define the inverse Fourier transform. So inverse Fourier transform. So if the Fourier transform of f of t is capital F of omega, then the inverse Fourier transform of capital F of omega will be f of t. So inverse Fourier transform of f of omega, this is equal to 1 by root 2 pi integration from minus infinity to plus infinity capital F of omega e to the power I omega x. And now the integration is with respect to d omega, and this is small f of t. So the Fourier transform of small f of t is capital F of omega, and the inverse Fourier transform of capital F of omega is small f of t. Okay, and here we have the coefficients 1 by square root of 2 pi, 1 by square root of 2 pi. In some other books, you might find some difference in this coefficient, but you should remember that the product of these two should always be 1 by twice pi. So in some books, you will find that here the coefficient is 1, and here the coefficient is simply 1 by twice pi. Okay, so different authors might use different representations here, but you should always remember that this coefficient and this coefficient, their product should always be 1 by twice pi. Okay, and if you compare this with our Laplace transform, you can see that we have the square root of -1 imaginary number I here. We have an I here, minus I here, plus I here. Okay. I think I made a mistake here. This is not x, this should be t. Since this is t, this should be t. Okay. Omega is integrated over, so what remains is a function of t. Fine. Then, what are the sufficient conditions for the existence of Fourier transform? So, let us write down. Okay. Let me pause for a second. So if you compare this with the Laplace transform, you see that we have a minus I here and a plus I here. In Laplace transform, you have e to the power e to the power s times t minus s times t, here e to the power plus s times t. Okay, here we have one extra I term here. There is difference. And what are the conditions for the existence of Fourier transform? So existence of the Fourier transforms. Fourier transform. Existence of the Fourier transform. So let me write down the sufficient conditions. So following are the sufficient condition for the existence of Fourier transform. Existence of Fourier transforms. Okay. So what are those? First, we have the function f of t is piecewise continuous. On the interval -infinity to +infinity. Okay. And what is the second condition? The second condition is that f of t is absolutely integrable. Absolutely integrable on the x-axis. That is the integral from -infinity to +infinity. The integral from -infinity to +infinity. F of t absolutely means we should take the absolute value, that is the modulus dt. This integral should converge. Okay. So these are the conditions for the existence of Fourier transforms. F of t is piecewise continuous in the range of integration. We had a similar condition for Laplace transforms also. And f of t is absolutely integrable on the x-axis or x or t-axis. Here we have written x-axis since we have defined it in terms of t. So let me write it as t-axis. T-axis from -infinity to +infinity. Okay. So let us look at one example. Let me take a new sheet of paper. Okay. Here, let us discuss one example. Let us find the Fourier transform of the function f of t equals e to the power minus a modulus of t. Okay, and here a is a constant which is greater than 0. So let us first find the Fourier transform of this function. So the Fourier transform of this function f of t is, by definition, we have 1 by √2 pi. We have this normalizing factor. Then we take the integration from -infinity to +infinity of the given function, that is e to the power minus a modulus of t, and multiply by e to the power minus I omega t, and integrate it with respect to t. Okay, this is the integral. Now this integral is with respect to t from -infinity to +infinity. And since we have a modulus of t here, what should we do? We should divide this range of integration into two intervals. One from -infinity to 0. So let me write it here. So we should divide the range of integration into two intervals. One from -infinity to 0 and another from 0 to infinity. Okay. So first, let us take the range from -infinity to 0. So in the range from -infinity to 0, t is a negative number. So if I take the modulus of a negative number, this is equal to minus t. So modulus of t will be minus t. Then that minus and this minus, they will cancel out, and we should get e to the power at. Okay, this is fine, e to the power at. Then we have this multiplying term minus I omega t dt. Okay, next let us consider the range 0 to infinity. So this means t is a positive number. Here t is a positive number. And if we take the modulus of a positive number t, then that is simply equal to t itself. Okay, so that is simply equal to t itself. So this becomes e to the power minus a t, e to the power minus I omega t dt. Okay, so the important point here is that if t is negative, modulus t is minus t, and this minus and minus, they become plus. And when t is positive, modulus t is simply equal to t. So we have t here. And this minus is from this minus sign. Okay, now we can easily perform this integration. So this is 1 by root over twice pi integration from minus infinity to 0. Now we can combine these two. So this is e to the power a minus I omega times t dt plus 1 by root 2 pi integration from 0 to infinity. If I combine these two, I get e to the power minus a plus I omega times t dt. Now this integral is simply equal to, e to the power a minus I omega t divided by the coefficient of t, that is a minus I omega. Okay, and we insert the limits from minus infinity to 0 plus 1 by root 2 pi. So this is from minus infinity to 0. Then this is 1 by root 2 pi. If I integrate this, I should get e to the power minus a plus I omega times t divided by the coefficient of t, that is minus a plus I omega. And the integration range is from 0 to infinity. So we take from 0 to infinity. Okay, this is fine. Okay, now let us insert the limits. We see that this constant a is greater than 0. Okay, so since a is greater than 0, a is a positive number. That means when we put t equal to minus infinity here, it becomes e to the power minus infinity plus I omega times infinity. So e to the power minus infinity is 0. So at the lower limit, this term is 0. Okay, I repeat, at the lower limit, this term is 0. At the upper limit, this term is 1. E to the power 0 is 1. Okay, so we have, this is 1 by root 2 pi. This is 1 by a minus I omega, because at the upper limit, this is e to the power 0, that is 1. At the lower limit, this is 0. Plus 1 by root 2 pi. Now, at the upper limit, at the upper limit, when t equal to infinity, this is e to the power minus infinity, which is again 0. Now at the lower limit, this is e to the power 0, that is 1. So we have 1 by root 2 pi, 1 by a plus I omega. Okay, this is fine. Now if I take 1 by root 2 pi common, 1 by root 2 pi, I should get 1 by a minus I omega plus 1 by a plus I omega, and that is simply equal to 1 by root 2 pi. Now, if I combine these two, this becomes a minus I omega whole into a plus I omega, and that is simply a square plus omega square. And then here we have a plus I omega plus a minus I omega. That means we have twice a. Okay, so this is the Fourier transform of the given function e to the power minus a modulus of t. We can call this some capital F of omega. This is a function of omega. We can call this capital F of omega. Okay, this is fine. Okay, now let us look at another example. We can look at another example, and one second. Okay, and that example is example number 2. Okay, that example number 2, that is find the Fourier transform of the given function f of t. This is piecewise function. It's 1, 0. So this is equal to 0 if modulus of t is less than or equal to 1. Sorry. This is equal to 1 if modulus of t is less than or equal to 1, and this is equal to 0 if modulus of t is greater than 1. Okay, this is fine. So let us find out the Fourier transform of this function. The Fourier transform of this function f of t is equal to 1 by root 2 pi integration from minus infinity to plus infinity f of t e to the power minus I omega t dt. Okay. Now, since the given function is a piecewise continuous function, and we are given the ranges of t, what should we do? We should divide this range of integration into these ranges, into these intervals which are given here. So first we shall divide it into, so first let me write it like this, 1 by root 2 pi, let me take it common. Then let us divide the range of integration into 3 parts, okay? 1 from minus infinity to 0, minus infinity to 1. So from minus infinity to 1 plus another from, sorry, this should be minus 1. Because this is modulus of t, okay? Then another from minus 1 to plus 1. Then the last from plus 1 to infinity. Okay, so we should divide this range of integration into the intervals according to this given ranges. So when t is equal to, when t lies between minus infinity and minus 1. So this is, first let me write everything here, e to the power minus I omega t dt. Here also f of t e to the power minus I omega t dt. Here also f of t e to the power minus I omega t dt. Now when t lies between minus infinity and minus 1, that means modulus of t is greater than 1. Modulus of t is greater than 1, and in this case f is 0. So in this case this f is 0. So this is integration of 0. And this is a definite integral. So the definite integral of 0 is still 0. So this is 1 by root over twice pi. Over twice pi. This first term, it is 0. Now let us look at the last term. This is integration of ft when t lies between 1 and infinity. When t lies between 1 and infinity, that means modulus of t is again greater than 1. So also in this case, it is 0. So here also f of t is 0. So these two terms vanishes. I repeat, these two terms vanish. What remains is only this term. So this is minus 1 to plus 1 f of t e to the power minus I omega t dt. Okay, this is simple. Now let us calculate this integration. Okay, so this integration here when t lies between -1 and +1, when t lies between -1 and +1, so let me write it here, 1 by root 2 pi integration from -1 to +1. What is the value of ft when t lies between -1 and +1? When modulus of t is less than or equal to 1, ft is 1. So this function is 1. This function is 1. So in this range, we simply have e to the power minus I omega t dt. Okay, because in this interval the function is 1. Now let us calculate this integration. This integration is simple. So we have 1 by root over twice pi. So integration of this is e to the power minus I omega t divided by the coefficient of t, that is minus I omega, and we take the limits from -1 to +1. Okay, and this is equal to 1 by root over twice pi. I can take minus I omega outside, so minus I omega. Then this becomes, first let us substitute the upper limit, so e to the power minus I omega, and then we have minus from the formula, then we insert the lower limit, e to the power I omega. Okay, now if I multiply this by this minus, what do we get? We get 1 by root 2 pi. So let us multiply this by minus I, then these two will interchange. So 1 by omega, this is e to the power, this will come first, I omega minus e to the power minus I omega, because I have divided by minus I here. If I multiply and divide by 2, if I multiply and divide by 2, what do we have here? This is sine omega. Okay, this is the formula for sine omega. Okay, and this 2 and 1 and this 1 by root 2, they will cancel out. We'll have root 2 by pi. So this is 2 by root over 2 by pi. This becomes sine omega divided by this omega, So this is the Fourier transform of the given function, this. Okay, let us look at another example. Example number 3. Find the Fourier transform of the function f of t is equal to e to the power minus at u of t. And what is u of t? U of t is the unit step function, where u of t is equal to the unit step function. This is equal to 1 when t is greater than or equal to 0, and this is equal to 0 when t is less than 0. This is the unit step function which we discussed earlier in our Laplace transform. So let us find the Fourier transform of this function. So to find the Fourier transform of this function, Fourier transform of e to the power minus at u of t. This is equal to, by definition, 1 by root twice pi integration from minus infinity to plus infinity e to the power minus at u of t e to the power minus I omega t dt. Okay, now let us divide the range of integration. Let us divide the range of integration according to this given interval. So t So first we shall divide this range of integration from minus infinity to 0 and then from 0 to infinity. So when t lies between minus infinity and 0, the function is 0. Ut is 0. Okay. So in the range minus infinity to 0, this function ut is 0. Okay. And in the range 0 to plus infinity, ut is 1. Okay. So let me skip that step and write it straight away from 0 to infinity. This is 1. So we have e to the power minus at, e to the power minus I omega t dt. Okay. Because in the interval from minus infinity to 0, this function is 0. So it will not contribute to the integral. And this is equal to 1 by root over twice pi integration from 0 to infinity e to the power, this I can take common, minus a plus I omega times t dt. This is equal to 1 by root over twice pi. Then integral of this is e to the power minus a plus I omega t divided by the coefficient of t minus a plus I omega. And the limits of integration are from 0 to infinity. Now, when we put t equal to infinity, this becomes e to the power minus infinity. Here we should mention that a is greater than 0. Okay, here we should mention that a is greater than 0. So when a is greater than 0, when t is equal to infinity, this becomes e to the power minus infinity, which is 0. So at the upper limit, this term vanishes. At the lower limit, when t is equal to 0, this becomes e to the power 0, and e to the power 0 is 1. So this simply becomes 1 by root over twice pi 1 divided by a plus I omega. Okay, so this is the Fourier transform of the given function e to the power minus at ut. Okay, now let us look at properties of Fourier transform. So let me write it on a new sheet of paper. Properties of Fourier transforms. The first property is the linearity property. Linearity property, or the linearity theorem. Okay, so the first property is the linearity property or the linearity theorem. We had a similar linearity property for Laplace transforms. So Fourier transforms, they also satisfy the linearity property. That is, Fourier transform of C1 F1t plus C2 F2t. This is equal to C1 times the Laplace transform of F1t plus C2, sorry, this is the Fourier transform, not the Laplace transform. So C1 times the Fourier transform of F1t plus C2 times the Fourier transform of F2 of t. This is the linearity property, provided the Fourier transforms, of F1 and F2 exist. Okay, and how do we prove this? The proof is very simple. Let us find the Fourier transform of C1 F1t plus C2 F2t. This is by definition 1 by root over twice pi. Okay. Then integration from minus infinity to plus infinity. We have C1 F1t plus C2 F2t multiplied by e to the power minus I omega t dt. Okay. Then since integration is a linear operator, we can easily take C1 outside. So this is equal to C1 multiplied by 1 by root 2 pi integration from minus infinity to plus infinity f1t e to the power minus I omega t dt plus C2 times, okay, I can use a bracket here for simplicity, times C2 1 by root twice pi integration from minus infinity to plus infinity here f2t then multiplied by e to the power minus I omega t dt. Okay, so this is C1 and this is nothing but the Fourier transform of f1t. So C1 Fourier transform of f1t plus C2 Fourier transform of f2t. Okay, this is fine. So we have proved that the Fourier transform of C1 f1t plus C2 f2t is nothing but C1 times the Fourier transform of f1t plus C2 times the Fourier transform of f2t. So here we have proved the linearity property. Okay. Then there is another property which is called the shifting property. So shifting property, let me write it on a new sheet of paper. Okay, I think let me pause the recording now.